continuing our conversation about energy, let's talk about one other conservation law, conservation of energy. So we talked about conservation of momentum and conservation of angular momentum. So this is another one of conservation laws. So conservation of energy says that energy cannot be created or destroyed, but can transfer between different systems or between objects and change from one kind to another. So basically, just like with the other conservation laws, we're going to start writing this as E total initial is equal to E total final. Now remember that energy is a scalar, and so writing the conservation of energy is actually significantly simpler than dealing with, let's say, conservation of momentum or conservation of angular momentum, because we also had to worry about directions, components, and so on. So here we don't have to worry about that. Okay, so this has to do with total energy. Now remember that we listed a whole bunch of different types of energies in the last set of lecture notes, and technically speaking, when we say total energy, it means total of all of those. But because we're only talking about mechanics, at least for the time being, we don't have to really worry about things like nuclear energy and electronic energy and chemical energy. It's implied that all of those other kinds of energy are going to stay constant if we're talking about mechanics. And so really we only need to be concerned with mechanical energy, because that's the kind of energy that's going to be the easiest to change under mechanical conditions or mechanical situations. So for mechanical energy, remember we consider kinetic energy and potential energy. So I could also write this as K initial plus U initial is equal to K final plus U final. Now in this equation, or in this version of it, I'm not distinguishing different kinds of kinetic energy or different kinds of potential energy. So that part depends on the situation and depends on the system and what else is going on. So let me box this first. Okay, so this is what we call conservation of energy equation. So again, be careful with what you mean by initial and final. Make sure that you distinguish between different kinds of energies and between different objects if there are multiple objects that make a system. Let's look at a very simple example. So a ball is launched at a speed of 30 meters per second upward. Calculate maximum height. So this is a very simple problem. It's actually significantly simpler than some of the stuff that we've done lately. We could have done this back when we were talking about free fall. It's one equation, you know, one step, and then plug everything in, and then we're done. However, I want us to think about it specifically from the energy conservation perspective, because we need to see how we're addressing these changes from one type of energy to another. So I'll start by drawing a little schematic here. So I'm going to say that this ball is launched at initial speed, V initial, right, vertically upward, 30 meters per second, okay? And I'll just call this Y initial equal to 0. And what we're trying to figure out is how high the ball can go, so I'm going to call that Y max. Now you may also recall from what we learned about free fall is that at the maximum point of the trajectory, velocity is going to be 0. So this is not new. Setting up this problem is not new. We could, like I said, we could have done this with what we know about freefall. However, what's new is considering what kinds of energies are involved in this process. So if y initial is equal to 0, that tells us that gravitational potential energy is equal to 0. And if v is equal to 0 at the end, that tells us that kinetic energy final, I should probably call it v final, right? And then I'm going to write this as k final is equal to 0. There is no springs here. We don't have to deal with objects such as planets or stars or whatever separated by distance r. So this is all we need, right? So no rotation. I'm literally just going to start saying k initial plus ug initial is equal to k final plus ug final. So now I'm being a little bit more careful about what kinds of energy I'm considering. I can simplify this equation. Okay, simplify it by making certain terms equal 0. And then I can also plug in expressions for kinetic energy initial and for gravitational potential energy final. Let's cancel out m and let's solve for y final. So this is going to be v initial squared over 2g. So plug in 30 meters per second squared divided by 2 times 9.8 meters per second squared. Okay, so be careful with units and plug in these values into your calculator. So I get 45.9 meters. So you can see that the calculation itself is actually very simple, right? And in fact, we've done this problem before. Let's not worry about that. So what I'm trying to say here is we're considering different kinds of energy that change from one to another. So in the beginning, there was no gravitational energy, so it all started with just having kinetic energy. At the end, there is no more kinetic energy, and all of the energy is now in gravitational potential energy. So all of the initial kinetic energy got converted to the final potential energy. Okay, so that's what we mean by energy conservation. The total amount of energy doesn't change, but one kind can change into another. Let's take a look at another example. So in this example, we have a block moving at velocity VA. So we'll know the mass of the block. VA is equal to 1.2 meters per second. So this block, given an initial velocity, is moving with this velocity to the right, and then eventually it encounters a spring, horizontal spring, of negligible mass and a spring constant of 50 newtons per meter. So the block connects with the spring and makes the spring compress. So over here, I can call this x equals 0, and now this whole system moves in such a way that the spring is contracted beyond x equals 0. Okay? So for part A, we're going to assume that there is no friction, and we are going to calculate x final, as in by how much did the spring get compressed when the block hit it. Now, this is a collision problem, right? Inelastic collision, right? But it turns out that momentum conservation may not be the best thing here. Because in the beginning, the block obviously had momentum. And at the end, if we're talking about maximum compression of the spring, the whole system is, at least instantaneously, motionless. So in the beginning, there was momentum, and at the end, there was not. So momentum conservation doesn't apply because there are external forces, such as the force of the spring acting on the system. So in a lot of situations, we can think of energy conservation as long as we can justify it. And we haven't talked about it, but the only way that energy conservation is violated is when there is external work involved. We'll come back to that idea in a few minutes. So for now, we're just going to say there is no friction, therefore energy conservation applies. So we're going to set that up. I'll start by writing K initial plus US initial equals K final plus US final. Because everything is happening on a horizontal surface, we can set this up to be y equals 0. That's our reference point. So if everything is happening at the reference point, it means we don't even have to worry about gravitational potential energy. Everything is happening horizontally. However, springs are involved, so potential energy is going to be the energy of the spring. In the beginning, the spring is not stretched or compressed, right? It's at equilibrium, so there is not going to be potential energy of the spring. And at the end, kinetic energy is 0 because the system is instantaneously at rest. Okay? So let's plug everything in. Again, 1/2 mv initial squared equals 1/2 kx final squared. Again, be careful distinguishing between capital K for kinetic energy and little k for spring constant. I'm going to cancel out 1/2, and then I'm going to solve for x final. So x final is going to be mv initial squared over k, little k, and square root of all of that. So 0.80 kilograms, 1.2 meters per second, don't forget to square, and then spring constant is 15 newtons per meter. Again, I'm going to plug everything into my calculator and get 0.15 meters. Okay, so as the result of the block colliding with the spring is compressed by 0.15 meters. Now, as far as energy transfer is concerned, we can say the same thing. All of the initial kinetic energy of the block is converted to the final potential energy of the spring, or we can also say final elastic energy. Okay, so this is our relatively simple example in which there are no external influences are involved. Nothing that we need to worry about that. Okay, so this is part A. Hold that thought. We'll come back to this example in a minute after I define our next idea. So remember that we defined work as change in energy. And now when we're talking about conservation of energy, we're saying that E total initial is equal to E total final. Okay? But isn't this the same thing as saying delta E total is equal to 0? So that's also the same thing as saying there is no work. I'm going to be more careful and write it as external work. Okay? So energy conservation, the way that we wrote it, the way that we used it, is only possible if there are no external works involved. More specifically, this term comes from what we call non-conservative forces. So work done by external non-conservative forces. Okay, so think about it. Conservation of energy is in the absence of non-conservative forces. So if we have non-conservative forces, that means energy is not conserved. Yet, we can still approach a lot of these problems, even where there are non-conservative forces, kinda in the same fashion as we approach energy conservation problems. Okay? Let's define non-conservative forces first. I'll do it over here. So non-conservative forces are those where the total amount of work over a closed path is not equal to 0. So non-conservative forces are defined in such a way that when we have a closed path, that the total amount of work over that closed path is not equal to 0. So closed path means that initial point is equal to the final point. So for example, if you have to, let's say, go uphill, you start on the bottom, you go uphill, you come back down the hill to the same initial point as you started with. So initial point is equal to the final point. For example, gravitational potential energy would be the same in the beginning and the end. So whatever has to do with gravity does not fall under this category. So gravitational forces are conservative. So let's write down the very short list of non-conservative forces. Friction, always non-conservative. Okay. Air resistance. We talked about drag before, so that's where that would fall in. Tension. And push or pull by person or object. So in the presence of those kinds of forces, force of friction, air resistance, tension, or push or pull by a person or an object, we can no longer use that statement of energy conservation, because each one of those forces is going to contribute something to the system. So either give energy to the system or remove energy from the system. So instead, we use what's called work energy theorem, or work energy principle. I abbreviate it as WET, work energy theorem. And it's basically the same thing, except now we're saying that work done by external non-conservative forces is not equal to 0. So I would address that by adding an additional term to my equation. All the other considerations, whatever we said about kinetic energy, potential energy, and so on, all of the other considerations stays the same. I'm just adding this extra term. And I'm not writing it, but again, this external work, that's work done by non-conservative forces only. How do we find this work? Well, remember, we defined work as force times displacement times cosine theta, right? So that was our definition of work. So if we have force vector and displacement vector, and we know the angle between them, we can figure out this external work. And again, remember that what we're doing here is looking at these forces, right? So that's what's going to contribute to this external work. Having said that, let's go back to this previous example. So everything's going to stay the same, except we're going to add friction to it. Okay? So now, let the coefficient of friction to be 0.5, and we're going to still calculate maximum compression of spring. So obviously friction is non-conservative, right? So we're going to have to address that. Let's draw a free body diagram. So before this block hits the spring, that's actually very important. So this should be a piece of cake for you now, because we've done all kinds of stuff with free body diagrams, right? So we have velocity to the right, so force of friction is going to be to the left. Okay. So force of friction, we only need free body diagram to figure this out, is going to be mu times the normal force, which we're going to write as mu mg. And why do we need force of friction? Because we have to figure out what this work done by force of friction is. I'm going to use subscript FR because I don't want you to think about it as final. There is no work initial or work final. It's a change, right? It's a transfer. So this is going to be force of friction times displacement times cosine of 180 degrees. By the way, this is actually a lot more general than just application for this problem. But work done by force of friction is negative force of friction times delta x. I'm actually going to box this. We can use that in the future as well. Okay? All right. So let's do the same thing as we did before. K initial plus US initial plus work done by force of friction, since there are no other non-conservative forces here, equals K final plus US final. We can make the same simplifications here as we did for the first part of the problem, and then we can make all the substitutions. 1/2 mv initial squared minus, I'm gonna plug in mu mg for force of friction, x final for delta x, right? Okay, look at the picture again really quickly. So displacement as the spring is compressing is equal to x final, right? Because the mass is going from x0 to x final. You can even write it like this if you want. Okay? And then this is all equal to 1/2 kx final squared. Let me plug in everything that we have, and I'm going to rearrange this a bit. 1/2 kx final squared plus mu mg x final minus 1/2 mv initial squared. Okay. Plug in all the values. K was 15 newtons per meter. We're solving for x final. Plug in mu, plug in mass, plug in g. Again, solving for x final. Plug in all of the other values. Okay, all of this stuff is equal to 0. So it's obviously a quadratic equation, so you're going to have to use quadratic formula. I'm just going to write down the answer. X final is 0.092 meters. Okay. Now remember that in part A, we had x final being 0.15 meters. So is that expected? That x final now is less than what it was before? Remember, there is friction present, right? Also, remember, work done by force of friction, we even got this part. Oops. Okay, we wrote this as negative. So this negative sign means that friction, as well as drag and resistance and all of those other forces, they always take energy out of the system. So because part of the initial energy was lost due to friction. When I say lost, I mean went outside of the system. Because of that, the final compression of the spring is now smaller than it used to be. So this conclusion here, that friction takes energy out, is actually very important, and it's one of the more general conclusions. So be on the lookout for those kinds of things. Be on the lookout for non-conservative forces and pay attention to what those forces do to the system as far as either adding energy or removing energy.